students. In this lecture, we need to start talking about acids and bases. So first of all, what are acids? Well, there's a few different definitions for acids, and the first one is an Arrhenius acid. And Arrhenius said that acids are substances that, when dissolved in water, increase the concentration of H plus ions. Now, remember that a hydrogen atom is just a single proton with a single electron. So that's a little e and a minus symbol for electron, and a little electron cloud around the proton. So what happens when we take away the electron? Well, all we're left with is a hydrogen nucleus, and all that's in the nucleus is a proton. So an H plus is a proton, and that bugs students when authors and professors call H pluses protons, but really it's just the same thing. So H plus and proton, we use those two things interchangeably when we talk about what's left over there when an acid goes into water. Okay, so right here we have HCl, so that's hydrogen chloride in the gas form. So if you guys remember when we did the naming chapter, when it was HCl on its own in the gas form, it was called hydrogen chloride, but when we dissolved it in water, then we called it hydrochloric acid. So what happens is we pump this gas into water, and the HCl is going to separate, so it's going to ionize or dissociate when it dissolves into its ions. So it'll split up into H plus and Cl minus. And if we draw the Lewis structure for that, what we can remember is that it looks like that. So if the H plus takes off on its own, it's going to leave these two bonding electrons right here, which we call a bond, over to chlorine, and that's going to turn the chlorine into a chloride. So those two bonding electrons turn into non-bonding electrons, or what we call lone pairs, right there. And the chlorine has a minus charge. And then that just leaves the H plus. Okay, and also recall that AQ means what? It means that it's dissolved in water. It means aqueous. Now, a more general definition for an acid is the Bronsted-Lowry definition. And the Bronsted-Lowry definition just says that an acid is something that can donate a proton, or it can give away an H plus. And there's another example of the exact same thing written down here, but it's written in a different way. So chemists like to confuse students. Just kidding, we don't. But we do like to write things in different ways that mean exactly the same thing. So if you look below, you see that water is part of the equation, and it's written as one of the reactants here in this equation, whereas water is put above the reaction arrow in the reaction above. Now, it means the same thing. We have HCl, and we're dissolving it in water, and there's different ways that we can say that. So here we have HCl, and we're dissolving it in water, and here we say that this is a liquid because we don't say water dissolved in water. We wouldn't say H2O, AQ. And then we put those two things together, and what happens is HCl is going to release the H plus. So you can see that in the equation above. But the H plus doesn't really exist floating around on its own in the water. What happens to it is the H plus hops onto a water, and it becomes this guy right here. It becomes H3O plus, which is called hydronium. So the HCl, it comes apart into H plus and Cl minus, and we can see that here. We've got the HCl, so we have HCl, and we have HOH, which is H2O, and the electrons from the water are going to grab that H plus, and then what we get is H3O, and that has a plus charge, and then the chloride is left over, and that has a minus charge. So we have neutral here, and those are both charges of 0. And then over here we have +1 and -1, and when you add those up, you also have a net charge of 0. So we have conservation of charge there. So we have 0 net charge on the left-hand side and 0 net charge on the right-hand side. So another point here is that we use H plus and H3O plus interchangeably, and you're just going to have to get used to that. The fact that we can write these equations a bunch of different ways, the fact that we use H plus and proton, those two words, interchangeably, the fact that we use H plus and H3O plus interchangeably, the fact that we put H2O above the reaction arrow here, or you'll see it in the reaction there, or sometimes you don't see it at all. Sometimes the equation will just say AQ, and you have to assume that water is floating around in there. And that's just the way it works. So sorry about that, but get used to it, guys. Okay. So let's talk about strong acids. So we've got strong acids versus weak acids, and on this slide we're going to do some strong acids. So strong acids are acids that completely ionize or dissociate in water, and this means that they come apart into their ions. So come apart. Okay. So if we look back at the previous slide, we worked with hydrochloric acid here. And our hydrogen chloride, the HCl, completely came apart into H plus and Cl minus, and there was no more HCl floating around together. So that is a strong acid, and you guys will see that in the list of strong acids right here. So some others: nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid. Those will completely ionize, completely dissociate, completely come apart. So if we have HNO3, which is nitric acid, and we write the equation like this, we will put a one-directional arrow, and we would put H plus AQ plus NO3 minus AQ, and NO3 minus is one of our polyatomic ions. That's nitrate. So HNO3 completely blasts apart into H plus and NO3 minus, and we don't have any HNO3 stuck together floating around in the beaker. And the one directional arrow is telling us that. We can see this with hydrochloric acid if we look at the beakers below. When we throw HCl into water, all of it comes apart into H plus and Cl minus, and the H pluses, they're going to hop onto the water, and you see that right there. And you don't see any HCl's that are stuck together still floating around in that water. You just don't have them. The HCl completely ionizes. It completely dissociates. It completely comes apart. Okay. Now, if you don't like the H3O plus and the Cl minus written in letters, here you guys go. Here's a picture of it right here. Okay. Also, another way that we could write this is H3O plus our nitrate ion over there. So yeah, again, you guys are just gonna have to get used to the H plus and H3O plus thing. Now, strong acids, they will burn us like we expect them to burn us, so you guys can see that here. And strong acids will also behave as strong electrolytes, and electrolytes are something we saw in another chapter. And if you put a couple of electrodes into a solution, the electrolyte helped move the charge, and it completed the circuit, and it lit up the light bulb. So if you remember, that's what happens. Strong acids will behave as strong electrolytes. Now, weak acids. Weak acids are acids that only partially come apart when you put them in water. So they only partially ionize or only partially dissociate. And an example of this is acetic acid. So acetic acid is right here. It's also right here, and it's also right there. So we see that it's written in a couple of different formats. So this format right here is the condensed format. And notice how it splits up the carbons into two different spots, and it also splits up the hydrogens into two different spots. And that's because it's identifying for you the structure of the molecule. So the CH3 on the end, it's indicating that we have something that looks like that. And then we have another carbon bonded to that carbon. So we don't have carbon and then three hydrogens in between and then another carbon. It's saying we begin with a CH3 unit and then the next thing over is a carbon. And then you see how it says OO. It doesn't mean carbon and then two oxygens and a hydrogen. What it actually means is you've got a carbon double bonded to an oxygen, and then you have another oxygen here, and then you have a hydrogen right there. And having the hydrogen on the end right there, that's indicating that it's different from these hydrogens over here. And this is our acidic hydrogen, or our acidic proton. That is the hydrogen that will come off and become H+. So the hydrogens on the left-hand side of the acetic acid, they don't come off. Carbon does not like to release its hydrogens. It will not do that, okay? Oxygen is totally fine to release a hydrogen. Now, in this version over here, there's a carbon at the end of the stick, and there's a carbon wherever you see a little bend in the chain, and then you just assume that this carbon has three hydrogens on it, because we know that carbon likes to have 4 bonding pairs, so we can assume some hydrogens there. So there are a bunch of different ways to write it. Now, okay, so since acetic acid is an acid, it's going to release H+, and we just said that this is the acidic proton right there. That's the H+ that's going to jump off. Okay, so we put it in water, and that H+ will jump onto a water, and it's going to leave us with this right here. And if we redraw that, what that looks like is this. Okay, so it's this guy right here without the hydrogen, and it becomes negatively charged because you took away its H+. Now, right here, AQ is saying that there's water sitting around, so we can go, okay, well, we've got acetic acid plus some water, and that H+ is going to hop on that oxygen right there, and that's going to give us our H3O+. The double arrows right here. Notice that when we did a strong acid, we had the single directional arrow that just showed us all of the reactants were going 100% to products. Well, the double arrows right there are telling us that we're going to come to an equilibrium where we have a certain amount of this left over, as well as our products. So not all of our reactant, the acetic acid, is going to go to the acetate ion and the hydronium ion. You're going to have all 3 of those, as well as H2O, sitting in your beaker, okay? Because they're weak acids, so they don't like to give off a whole lot of H+. They just give a little bit of H+ away, and then the rest of your acid just sits around and is like, I'm done, I don't want to do anymore. So some other examples: phosphoric acid, so H3PO4, carbonic acid, hydrocyanic acid, and benzoic acid. This is benzoic acid right here. So you see this C6H5 on the end there? That is this ring. So you have 6 carbons in the ring, and each carbon has a hydrogen on it, except for that carbon right there, because it has this COOH unit stuck to it, okay? And this one right here, this hydrogen, that's your acidic proton, that's your acidic hydrogen because it's connected to an oxygen. And it's not one of the hydrogens connected to the carbon. Because remember, carbons do not like to release their hydrogens. Oxygens are okay with that. So what does a weak acid look like if we put it in a drawing? Well, HF is a weak acid. So that's hydrofluoric acid. So we can write the equation like this. So we've got hydrofluoric acid in water. So you guys can see you're putting it in some water. And it's a weak acid. So not all of it is going to come apart. So you've got some HF still sitting around in this water, in your solution. But it does give off a little bit of H+. And that means that it's going to give off a little bit of F- because if you give off H+, you got to give off F- because HF is all you got there. And we can also write H+ as what, you guys? As H3O+, okay? Because we're assuming that we've got water there, and the H+ actually doesn't exist on its own. It hops onto a water to become hydronium. So again, the double arrows, you guys, those are indicating to you that you still have your reactant sitting there in the beaker, okay? So you have some of your product and you have some of your reactant, and they come to an equilibrium. Okay, that brings us to polyprotic acid. Now, poly means what? That means many. And protic means proton. And in this case, we're talking about the H+ version, how we think about acids. So this is talking about acids that have more than one H+ to give away. So if you have two of those, you're called diprotic, and if you have three H+ to give away, you're called triprotic. But all together, we call those polyprotic acids. So they've got many H+ to give away instead of just one. Okay, so acids that can release more than one H+. And an example is sulfuric acid. So sulfuric acid is H2SO4. So you can see right there it's got a couple of hydrogens to give away. So what happens is we're going to put sulfuric acid or we're going to put H2SO4 in water and it becomes sulfuric acid. How do I know that's what's going on? Well, right here it says AQ. So whatever I have over here, if I've got AQ behind it, it means I've put that in water. And if I put that in water, the acid's going to release an H+ because that's what acids do. And if H2SO4 gets rid of one of its H+, it's going to become H1 or just HSO4, and it's going to have a -1 charge on it because it lost one of its pluses. And where does the H+ go to? Well, it hops on a water. So if you guys need to write H2O over here, just so you know how you got an H3O+, that's totally okay. Also, if you're comfortable with the fact that AQ means that there's H2Os floating around, you're okay to leave it off of this side. Chemists often do that. Okay, so we have HSO4- and we have H3O+ on the other side. And again, we have neutral and neutral, and over here we created a -1 there, so we must have created a +1 there because we have to have conservation of charge. So net neutral over here and net neutral on the product side because -1 and +1 add up to what? 0. Okay. So the thing about HSO4- is that it can float away in the beaker, la 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 la, it takes off, and on its travels it can find another water. And the water's like, hey, you want to give me that hydrogen right there? I see you've got an acidic hydrogen. And the HSO4 says, no, I don't really want to, because when I was H2SO4, I gave away one of my hydrogens, and I really wanted to give away my hydrogen because I was a strong acid. So you guys see the single directional arrow over there. And so the HSO4 is a whole lot weaker than the H2SO4, so it's a weak acid. So when it meets water, it doesn't always give away its hydrogen. But when it does, it turns into SO4 minus 2, which is a polyatomic ion that we've seen before. This is sulfate. And that hydrogen on the SO4 hops onto the water to give us H3O plus, which is what? Which is hydronium. Okay, so H2SO4 has two hydrogens it can give away. It'll give away the first one, no problem, but that second one doesn't like to come off a whole lot. And you can see that with a double-headed arrow right there. It's indicating that HSO4 is a weak acid, and so you're going to have a lot of this sitting around, and it's not going to completely dissociate. All right, so let's do a problem. Let's write out the equations for the ionization of phosphoric acid in water. So phosphoric acid is H3PO4. So what we want to do is we want to write H3PO4. Now, what we've been doing is just writing the acid and then writing AQ after that and just assuming that water is there. But this time, let's just go ahead and write the water there so we can just practice doing it differently. So phosphoric acid needs water, and phosphoric acid is an acid, so it's going to want to give away a what? An H plus, because that's what acids do. And the weird thing about phosphoric acid is it's a polyprotic acid. You can see all three hydrogens right there, all three acidic hydrogens. But phosphoric acid doesn't like to give away any of those three hydrogens. It's not like sulfuric acid where the more hydrogens it has, the stronger it is. H3PO4 on its own is already a weak acid, which sounds strange. It looks like it should be a super acid because it has three hydrogens, but nope. So we're going to want to write the double arrow there. And we'll learn about which acids are strong acids and which acids are weak acids in a later lecture. But just for now, trust me, phosphoric acid is a weak acid. So what happens, nonetheless, because it's an acid, is the water is like, hey, phosphoric acid, you're an acid, so you're going to give me a H plus. And phosphoric acid says, certainly I can do that. And that means that water grabs an extra H plus and it becomes an H3O plus. And our other product is H3PO4 without one of the hydrogens, which makes it H2PO4. Now, H3PO4 is neutral, and it lost one of its pluses. So if you're neutral and you lose one of your positive charges, you're going to become what? You're going to become a negative charge, a -1. And the other way we can think about this is what we talked about before. H3PO4 is neutral, water is neutral, so you have a net neutral charge on the reactant side, on the left-hand side. And you have to have conservation of charge, which means that on the product side, you have to have a net charge of 0 also. Well, H3O plus is always +1, so that should indicate to you that your other product is going to be -1 because you have to have conservation of charge. And a +1 and a -1 together make what? 0. Okay, so a net neutral charge. All right, so that's the first reaction that happens. Now, H2PO4 can swim away. It's like, okay, that was fun, you guys, but see you later. It swims away in the beaker because we have a giant beaker here full of water. And it's floating along, living its happy life. And it meets another water along the way. And if H3PO4 was a weak acid, then H2PO4 minus is definitely a weak acid. It's weaker. So we're going to have another set of double arrows there. And H2PO4 minus 1 meets a water, and the water's like, hey, You want to give me your H plus, and H2PO4 minus is like, not really, but okay, I will, since I'm still an acid. And water's like, yippee, okay, jump on board, H plus, and that makes it become H3O plus. So this is doing another reaction. And if H2PO4 minus loses an H plus, it goes to HPO4. And if H2PO4 minus 1 loses one of its positive charges, then it's going to end up as HPO4 with what charge? -2. Okay. Again, conservation of charge. H2PO4 minus 1 has a -1 charge. And H2O is neutral. So over here we have a net charge of -1. So over here we need to have a net charge of -1 also, because we need to have conservation of charge. And this makes sense because H3O plus is always +1, and +1 minus 2, that gives us -1. So our charges check out. All right. So that happens, and the products are like, okay, let's go on our merry way. And HPO4 minus 2 does that. It's like la 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 la, swims around in the beaker, and it comes on over here to the left-hand side of the beaker, so I can write another reaction for you. So we have HPO4 minus 2 here. It swims away and it meets another water, because remember, we're sitting in a beaker full of water, you guys, so there's tons of water molecules. And the water molecule says to HPO4 minus 2 what? It says, hey, can I have that hydrogen you've got there? And the HPO4 minus 2 is like, no, I really don't want to do that. I'm already at a -2, and that's a whole lot of negativity, and I really don't want you to take away my positive charge. But occasionally water bugs so bad, the HPO4 minus 2 will give in. It's like, okay, just take it and go away. So HPO4 minus 2 is an even weaker acid than the above two acids. So we're definitely going to have the double arrows there. And if H2O grabs an H plus, it becomes what? It becomes H3O plus, and hydronium's always +1. And remember, you can just write plus, or you can write +1 when you have +1. But if it's plus anything else, like +2, +3, +4, you got to write the number. And that's going to leave us with what? So HPO4 minus 2 loses its H plus. So all we're left with is PO4, and that's going to have a charge of what? Now it's going to be -3. And that's somebody that we've seen before. That's our polyatomic ion phosphate. Aha! Something we've seen before. And those are the three equations that we can write for the polyatomic, for the polyprotic acid H3PO4. Now, another little quirk here, you guys, it doesn't matter if you write hydronium first in the products or the other product. So I could have written PO4 minus 3 first and then written plus H3O plus. Doesn't matter at all. This reaction gives off these two products and they go swimming around in the beaker. It doesn't matter which order you write them in there, okay? So there are the equations for our polyprotic acids. All right, on to bases. So an Arrhenius base, it's a substance that when you dissolve it in water is going to give off hydroxide ions. So if we have the base sodium hydroxide there, it's going to ionize, or it's going to dissociate, and it's going to increase the concentration of hydroxides. So we're going to get the sodium ion Na+, and we're going to get hydroxide here. And hydroxide we saw in the polyatomic ion chapter also. So you've seen that before. And if you guys need the lone pairs drawn in there, there they are. We just don't draw them sometimes because we assume that you know that they're there. Okay? All right, so there's also a Bronsted-Lowry definition for a base, and the Bronsted-Lowry definition for an acid was somebody who gives away a proton, so a proton donator. So the Bronsted-Lowry definition for a base is a proton acceptor. And remember, proton is the same thing as H+. So it's some kind of something that likes to scoop up H pluses. So if we take a look at this acid reaction that we saw before in the acid slides, what you see is you have hydrogen chloride, the acid, so the Cl is here and the H is here. And then we have water here. And what happens is that the water accepts this H plus right here and becomes the hydronium ion. So the water is behaving as a base here. It's grabbing that H plus. So in the Bronsted-Lowry base definition, water's behaving as a base there. So right here, HCl is the proton donor and water is the proton acceptor. When you pair water with an acid, water will behave as a base. When you pair water with a base, water will behave as an acid. And we'll see that when we do acid-base reactions pretty soon. So that brings us to strong bases. So strong bases, like strong acids, are going to be things that completely ionize or completely dissociate in water. Now, strong bases are going to cause a large concentration of hydroxide, OH-, and we can see that right here when we look at this beaker picture. We have sodium hydroxide, and when you put it into water, it's going to separate into Na plus and OH-. So all of a sudden, bam, we have a whole lot of OH- in that water. So we definitely have a basic solution there. And here's a list of our strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, those are all very common bases that you'll see in chemistry, especially these two. These ones over here, we don't see them as often. They tend to be a little less soluble than the ones on the left, but they will give off their hydroxide ions and cause a basic solution there. All right, so weak bases. Weak bases are like weak acids. They're only going to partially ionize in water, partially dissociate. So they won't cause as great of a hydroxide concentration increase as strong bases, but they'll still cause a lot of hydroxide to appear. All right, so the difference here often is that our weak bases are what I like to call sneaky bases. They're not things that you look at and you can see, oh, there are hydroxides there. So if I put that in water, it's probably going to release its hydroxides, like with the strong bases. So right here you can see the hydroxides. Oh, that is a base. There's hydroxide there. With weak bases, it's not so obvious. So if you look at ammonia right here, it looks like it would probably be an acid because it has a lot of hydrogens on it. But the thing about it is that nitrogen does not give away those hydrogens, so it doesn't act as an acid. What happens is you have your weak base in water. So say we have ammonia right here. And we have water right here. The lone pair electrons on the nitrogen will reach over and grab an H+. So it'll rip the H+ off of the water, and then the bonding electrons that are between the hydrogen and the oxygen, they will be released onto the oxygen to make non-bonding electrons, or a lone pair. And so what we get is the ammonium ion, and we've seen that before. It's a polyatomic, and that has a plus charge. And what's left is the OH right there. So we get OH minus, and ammonia doesn't have its own OH to release, but it causes the water that it's in to release the OH. So it behaves as a base because it increases the concentration of hydroxide. So that's why I like to call them sneaky bases, because it's not really obvious that they're bases because you don't see that OH. So if you want to identify weak bases, it's often the ones that contain nitrogen. So pyridine is another one. So pyridine looks like a really big, weird, and evil molecule, and how would I even know what this is doing and that it's a weak base? Well, if you notice, it's got this nitrogen right here. And the nitrogen is going to do the exact same thing that the nitrogen does in the simple molecule ammonia. When we put it with water, the electrons on the nitrogen will reach over and grab that hydrogen. They'll say, come here. And then those electrons that are between the hydrogen and the oxygen are going to fall back onto that oxygen, and it's going to make hydroxide. So what you're going to get is this ring here. And the ring will be exactly the same, except the nitrogen will pick up a hydrogen just like ammonia did, and so it'll have another bond and it will have a positive charge, and the other product will be hydroxide, OH minus. And if you increase the concentration of hydroxide in solution, you are a base. So it works exactly the same way as the ammonia does to cause this basic solution right here. So if we look at it in a beaker right here, what we'll see is that because ammonia is a weak base, we still have some of it hanging around in the beaker. We don't have 100% product, so it doesn't completely ionize into ammonium and hydroxide. We still have some of the original stuff around. So what we would do about that is write the double arrow. And again, that's indicating that when it reaches an equilibrium, we're going to have some of this stuff still sitting there along with our products. And you guys, the AQ is telling us what? It's telling us that everything is sitting around in water. And you guys can see that right here. It's sitting in a beaker of water. Here are, again, ammonia and pyridine. So we've got ammonia here, which is also written as NH3, just a bunch of different ways to write it. And pyridine we saw before, but it had its nitrogen on the bottom side. So it's this guy right here. We're just flipping it over so that the nitrogen is right here on the top, okay? And molecules slip around in the beaker all day long, so we can draw it differently. So pyridine drawn on this slide right here. It looks like this, and the white balls are hydrogens. And if it meets water, the H plus is going to be connected right there. And the one that we haven't seen is methylamine. And this works, again, exactly the same way as ammonia. But what we're going to have instead of the hydrogen on the bottom is we're going to connect a methyl group. And methyl is CH3. So you can write it like this, CH3. Or you can write it out so you can see the full structure of it like this. And you can see that right there. And that will also work exactly the same way as ammonia and pyridine did when you put it in water. So it'll meet a water, and the electron pair, the lone pair on the nitrogen, will reach over and grab the hydrogen. The electrons between the hydrogen and the oxygen will fall back on the oxygen, and what we'll get is we'll get a methyl ammonium ion, and I'll just write the CH3 in the condensed form down there, plus hydroxide, and we have increased the concentration of hydroxide in our solution, so methylamine is a base. Okay, so for the weak bases, again, you guys, look for something that has a nitrogen in it and looks like it might be an acid because it has all kinds of hydrogens, but realize it's not going to give away any of those hydrogens, so it's a base. All right, and then next lecture we'll go on to conjugate acid-base pairs, but we'll wait for the next lecture for that. So that's all I've got for you guys in this lecture, and I will see you next time. Bye-bye.